Hello everyone, this is Dr. Young, and in this video, it's a long video, but I'm going to talk to you about what an imine is, give you the overall reaction of how to form imines from ketones and aldehydes, and show you the mechanism of how these imines are formed. So get prepared for a long video, stop whatever you want, come back to it when you need to. But imines, just to start us out, imines are the functional group where you have a carbon double bonded to a nitrogen. That's what you're looking for. What's on this carbon can kind of vary. What's on this nitrogen can kind of vary. So let's take a closer look. Now, introduction to imines. Now, it's imines with an I, right? You may have learned about functional groups like amines, right? So here's an amine, here's an amine. Amines are typically classified as having either sp3 carbons on them or hydrogens on them. So like this nitrogen up here with this isopropyl group, this isopropylamine, we would consider this a primary amine because there's only one carbon group coming off of it, so this would be a primary amine. This second group over here is also an amine, but it has 1, 2, 3 groups coming off of it, so this would be an example of a tertiary amine. And now that's different than a imine with an I, right? So you have amines and you have imines. Imines are where you have a nitrogen double bonded to a carbon. So, right, this is sp2, not sp3. So that's kind of the big difference here, right? So an imine is when you have a C double bond N. It's kind of like a carbonyl, but with a nitrogen instead of an oxygen. And then lastly, to confuse things even more, these functional groups all sound so similar. You have amines, imines, and enamines. So enamines, which is where you have the ene stands for an alkene, and the amine stands for, right, something with a nitrogen in it. So that's when you have an alkene with a nitrogen directly attached to it. So it's kind of like an ene-al, where you had an alcohol on an alkene. An ene-amine is when you have an amine directly attached to an alkene. In this video, we are just talking about the imines with the I. So that's what we're going to be looking at here, right? So formation of imines, that's what we want to talk about. In other videos, I will talk about forming enamines, but this one we're focused on imines. So overall, what are we looking for here? You're going to have some sort of carbonyl compound. So here's your carbonyl compound. This is going to be an aldehyde or a ketone. The groups that are on this aldehyde ketone are not that important. It's just going to be an aldehyde or a ketone. So I have, right, this would be a ketone with 2 R groups. If there's an H on here, you'd have an aldehyde. You're also going to have an amine, right? So you're going to have some sort of amine. And now this amine can't be any amine. This amine has to be ammonia. It has to be ammonia, right, which is just NH3. Or it has to be a primary amine. It has to be ammonia or a primary amine. And when we look at the mechanism, we'll see why, but it's because we're going to lose 2 H's from it. So at most, that amine, that nitrogen, can only have 1 R group. It can have all 3 H's, or it can have 2 H's and be primary. But if it has 2 R groups and only 1 H, we cannot form an imine. We are going to form an enamine. And again, we'll talk more about that in a later video. And then if you combine those two, you're going to have some sort of catalytic amount of acid. What acid it is not that important, but you need a little bit of catalytic acid to help this reaction occur. And so we'll take a look at the mechanism here in a sec. Combine those two, heat them up for a little bit, remove some water, and you're going to form your imine product. So let's take a closer look at this mechanism. So here I have a specific example of a butanol, and I have an ethylamine. And I used sulfuric acid, and I wrote cat next to it just to signify that it's just a catalytic amount of acid here. So I'm going to go ahead and break up my strong acid into the H plus and the HSO4 minus, because that's really what I'm going to react here. And look at this mechanism, right? It's going to be kind of long and kind of hairy. The first thing you want to do is activate your carbonyl. If you take a look at your carbonyl compound, in this case I have an aldehyde, right? Definitely you have your oxygen that's partially negative. The carbon here is partially positive. Step 1 is going to be just protonate your carbonyl. So the partially negative oxygen is going to go pick up the H+, which is going to give us our protonated carbonyl, like I said. So now the oxygen is double bonded to the carbon, has one bond to the H, and is now positive because it gave electrons up. This does have a resonance structure, right, where I can draw it like this instead, where I have the electrons from the carbonyl go up to the O, right? Remember, oxygen is not exactly in love with being positive, so you can imagine that the positive is also being delocalized onto that carbon down there. The resonance structure on the right's better in the sense that you have a positive charge on the carbon, but much worse in the case that you have an incomplete octet. So it's somewhere between these two. Usually people use the one on the left as opposed to the one on the right. I don't care which one you do. But it's at this point that your amine adds. And again, I don't mind which one you start with. I'll use the one on the right just because I feel like it's a cleaner looking mechanism. However you draw it, totally fine by me. So now your amine, right, which was partially negative, so your nitrogen, right, has a partial negative here, partial positive on those hydrogens in that carbon. Your partially negative amine, of course, is going to be attracted to that positive carbon, or like I was saying, and you can ignore what I'm about to do if it muddies it for you. You could have attacked the resonance structure on the right or the one on the left, however you want to do it. It's just you're going to move either 2 arrows or 1 arrow. Either way you do this, you're going to end up with this intermediate here. Right, so now you're going to have, I have those carbons, I have an O and an H, right, because I either attacked the resonance structure on the right where I already had 2 lone pairs and the OH, or I attacked the resonance structure on the left, in which case you kicked up those pi electrons to the oxygen to make it neutral. There's still an H on here, and now my nitrogen is attached. It had 2 H's on it, and it has this ethyl piece. And so since my nitrogen was neutral before, it gave away electrons. Now it is the positive thing. So we have a positive nitrogen here. Now that nitrogen is not going to stay positive, right? It can take back electrons from something. It's either going to take them back from the H, or it's going to take them back from the carbon bond that it just formed, right? If it takes it back from the carbon bond that it just formed, we're going backwards. However, if we take it from the hydrogen, if we deprotonate it, that means that we are going to move forward to form a new intermediate. And remember that all these things are happening at once. They're all kind of just happening. There is no like inherent forwardness. It's just that things go back and forth and back and forth and back and forth. And then plus H plus. Again, I don't care that you write just a free H plus. It will probably be on some solvent molecule or another ethylamine from the beginning, but I'm fine with you just writing just a free H plus. And so now this H plus, right, is going to be attracted to something that's partially negative, right? Opposites attract. And so I have a partially negative O and I have a partially negative N. Now, normally we'd say that the nitrogen is a stronger base because it is, and so we'd protonate the N. But protonating the N just goes backwards a step, which happens, which is totally fine. But let's imagine, well, what happens when a minority of the time, let's say some of the time, we're going to have the oxygen get protonated. If the oxygen gets protonated, we form a new intermediate where now we have an O with 2 hydrogens that is now positive, still had that H on it, still has a nitrogen with an H, and that ethyl piece. And again, just like the nitrogen in a couple steps beforehand, the oxygen doesn't want to stay positive. It's got a formal charge, wants to try to get rid of something. It can take electrons back from the H, deprotonating, which means we're going backwards a step, or we can have water leave, right? We have water, and we've seen water as a leaving group before. It's very, very stable when it leaves. So it could leave, which again gives us a new intermediate. Now we have, I'm going to kind of rearrange things to draw them a little bit so we're looking like our product here. Now this carbon here is going to have the nitrogen with an H and a lone pair and this H, but we've taken water off, right? Water left that carbon. So now that carbon has a positive charge. And I rotated things a little bit, so if it's confusing, let me go ahead and number these. That's carbons 1, 2, 3, and 4. This is still carbons 1, 2, 3, and 4. I just swung the nitrogen up a little bit so that it looks more like the product that I drew up above it. But it doesn't really matter, right? These are all single bonds. They can all freely rotate, so please bear with me. Now, this nitrogen has a lone pair. We have a carbocation here. The carbocation is actually not that bad in terms of its energy because it's resonance stabilized, right? Because if you take a look at this, you can imagine this lone pair from the nitrogen dropping down to fill that previously unfilled octet, right? So I can draw a resonance structure here where that nitrogen is double bonded now with that carbon so that that octet is filled, but that makes this nitrogen up here positive. So I've got this resonance stabilized carbocation. Again, probably the intermediate drawn, the resonance contributor on the left drawn is better because it doesn't have any empty octets. You have full octets in that case. But now if you look at this, right, we're actually just one little step away from our product here. If you take a look at this, again, I have a positive nitrogen, which has an H on it, and so I can draw those electrons going back up, which is really just another resonance structure, or I can have this nitrogen get deprotonated, which is going to give us our product plus our acid back. And remember, our acid is catalytic, so that H plus can then go back and reprotonate that parent aldehyde, in this case, butanal, and do another reaction. So that H plus can react again and again and again and again. So overall, you're going to have H plus as a catalyst that's reformed, and we saw that we had water that was formed down, let's see, down here. Right, we formed water also. Now I wanted to point out here, I'll do this in green. I wanted to point out, remember that before I said that the type of amine that can form an imine has to have 2 hydrogens on it, right? And so here we have 2 hydrogens on this primary amine. And that's important because you lose a hydrogen here from the amine, and you lose a hydrogen at the very end from the amine. So you have to be able to lose those 2, right? This was my first hydrogen that I lost. This was my second hydrogen that I lost. And which is why secondary amines and certainly tertiary amines cannot form imines based on this mechanism. So that's an example of the mechanism of forming an imine. You'll notice that all these steps are reversible. We'll talk about on the next slide that if you want to reverse this whole thing, all you really do is you just add water and acid to an imine and everything goes backwards. Everything goes backwards. This is all a bunch of like Le Chatelier stuff, right? If you want to go forwards, you have to do this reaction, take water out. If you want to go backwards, you just put water in and it goes backwards. So let's take a look at a few examples of forming imines and undoing imines. So here we go, we have this aldehyde, we have again what looks like a primary amine. To go from part 1 to part 2 to your reactants to your products, all I'm going to do is I'm going to redraw my carbon skeleton, right? This is where I had the double bond O, only instead of drawing the double bond O, right? So I basically just took this whole piece right here, but not the oxygen, right? So I'm erasing the oxygen. And then I'm going to take my amine and put it, let me actually do this in blue, not that it really matters. If I took this amine, I'm going to take everything but those 2 hydrogens I just said were going to be gone in the mechanism, right? So erase those 2 hydrogens. And that means that I'm going to take my carbonyl, or my carbon-containing piece where it was a carbonyl, and I'm just going to put that imine there. So that imine, that nitrogen, and whatever its group was, in this case I had a CH3, so I'm going to draw a CH3. I'm going to draw that piece there, right? So I erase the O, and I put the nitrogen with whatever its R group was in its place. That's all I did. And then the other side product is water, but it's organic chemistry, we don't care about the inorganic stuff. Same thing if I do this, right? It looks like my carbonyl compound is here. It's just this acetone or 2-propanone. So I had the double bond that was an O, but now I'm going to attach the thing that had the nitrogen on it. Again, minus the 2 hydrogens. So now there's going to be a nitrogen here, but now with this cyclopentyl group on it. So I got a cyclopentyl group on that. And again, plus water, but I don't care about water. So I just made these 2 imines from these primary amines and a carbonyl. Notice that it doesn't matter if the amine is on the left-hand side or the right-hand side, who cares? The point is that you have a aldehyde or ketone, you have a ammonia or primary amine, and you have an acid catalyst. That's what you're looking for. Now, in this last case, this is undoing. This is the reverse reaction. So I'll write reverse reaction. Right, this is going from your imine back to your carbonyl, whatever that parent carbonyl was. And all you have to do that is to add water and acid, and they just unravel super quick. They do the exact opposite mechanism of the one I showed you on the previous slide. I'm not going to do the mechanism here because, again, it's literally the opposite. But what you do with that is you do just the reverse, right? So apparently the parent carbonyl was this thing. So instead of a double bond N, it's now a double bond O. And the amine that was probably added apparently was isopropylamine. So I'm just going to put the two H's back on that and draw the isopropylamine. All right, so that's where those two pieces came from. And so imines, well, I'll talk about this more in class, but those are one of the reversible reactions. They can go forwards and they're easily undone. You just add water and acid and those suckers unravel, is the idea. So I know this was kind of a lot and kind of quick, but that's the idea about how to make imines and how to figure out, can I make imines? Keep it out. In the next video, we'll talk about enamines, which are very related but slightly different because you don't have two H's to take off your amine. You only have one. So that changes the last step of the mechanism to an elimination, and you get an enamine instead. Anyways, hope you feel a little bit more comfortable about what an imine is. Study up, do lots of practice problems. Have a good night.